as he mentioned, my name's Alyssa Batula. I've been working with machine learning for about 7 years, and I'm going to talk to you about what are your first steps if you want to get started in machine learning, whether that's for a personal project or your boss has this great idea, our project could be better if we use machine learning, you're on that team. So a good first step is, what is machine learning and how is it different from what I was doing before? So I like this definition of machine learning. There's a million of them, but it's the science of you're getting computers to act without being explicitly programmed. So in traditional programming, you're telling the computer what to do line by line. With machine learning, we're teaching it to make decisions or take actions without programming each of those individual steps or telling it in this particular scenario you need to do this thing. And so we do this by showing it lots of examples. So it's kind of like whenever you're learning a new thing, especially like as a kid when you learn to tie your shoes, someone would show you how it's done, you'd try, they'd tell you what you did wrong, you'd try again. And so a kind of metaphor exercise that's often used with new programmers is, how do you teach a computer to make a sandwich? So the idea is that the instructor is trying to teach people that the computer is only going to do what you tell it and nothing more. So if you've never done this before, the students will try and write down what steps are involved in making a peanut butter and jelly sandwich, and the teacher will act them out and try and make it entertaining for the students when they realize they missed a step or two. So if you forget to say, take the peanut butter and jelly out of the jars, just put it between the bread, you might get something like this: 2 loaves of bread with some jars in between them. Or, okay, so you tell them to get the peanut butter out of the jar, and you forget to tell them to open the lid, you might start stabbing it with a knife because they didn't tell you you had to open the jar. And so this can get kind of entertaining, but it's also kind of where machine learning comes in. So when you're done with this exercise, like you've taught the students about being explicit with the computer, but you still haven't taught the computer to make a peanut butter and jelly sandwich. There's a million if statements. What if the knife is rotated 1/4 of a degree differently than when you learned to pick it up? What if the bread is in a different drawer because your sibling doesn't know where it belongs? Like, how do you teach a computer to deal with this? And so with machine learning, it's not actually a metaphor. There are people teaching robots to make, I'm not sure about sandwiches, but definitely pancakes and other foods. And so this is where that teaching by example instead of line by line every single if statement comes in. So back to our problem. You are the developer and you've been told, we're doing machine learning now. Where do you start? So the first step is not to start writing code, and it's also not to start memorizing a bunch of algebra problems. Your first step is actually to change your mindset. So you're not putting building blocks together to make something work. Like if you're making a website, there are tools out there that are pretty well known. You just need to pick the best ones for your circumstances and make them work and behave together. So you're doing more of gathering data and experimenting with different things to see if they work. And this can be a hard change, especially for project managers and people who want specific timelines, like I can build a website in X amount of time. But saying, yeah, sure, I'll have this machine learning program working in a month, it's hard to say. It could work on your first try and be done really quickly, or it could take a year to figure out how to get it working. So this is getting better as there's more off-the-shelf things available. Like people have solved some general problems, like getting text off a document. There are some things, Amazon has one, Google has one, where you can take an image and pull the text off of it. So there's some things that you can just use off the shelf. But if you're building anything on your own, it's much harder to predict a timeline. And so getting people to understand that can be a tough part. So some things to keep in mind. There's much more managing of data, organizing your data, double-checking that it's correct, all of that stuff. Finding the data in the first place, you might realize you don't have enough data to do a machine learning problem. And so now you're a programmer, and instead of writing code, you're looking for sources of data. I mentioned a little bit about all of the unknowns. So there's a lot of unknowns. You're running experiments to see what works. Just a lot more time experimenting and seeing, will this work, won't it work, rather than saying, yeah, I'm going to write that this week. You also need new ways to determine if what you're doing works. So there's new definitions for something that's good. So usually you write some code and you test, if I push button A, does action B happen? Or does the system crash? And there's still some of that because it's still a program running the code. But you need to also make sure your algorithm works on the whole. And this can be a problem with some people if you want to determine the difference between a cat and a dog. And you give it a picture of a dog and it says a picture of a cat. You don't actually know that your system's broken because you've only tested on one example. What if that is the only picture of a dog that gets wrong? You have to test on a lot of different examples and look at the overall picture. Usually it gets it right, or rarely it gets it right. And so it's a different way of determining whether or not something's working well. So, we talked about changing your mindset. The second step is still not code. It's actually determining if machine learning even makes sense for what you're trying to do. So some problems will work well with machine learning. They're a great fit, solve a lot of great problems. Sometimes the solution is actually better done with just traditional programming, maybe some clever if statements. And also just be careful if someone's asking you to do weird computer magic. Like just because machine learning is a thing, computers still aren't magic. I wish, but not yet. So, what is machine learning good at? It's good for things where you have lots of data to train on. So I've said a couple times, I'll probably repeat myself many more times, but you're teaching it from examples. So you need a lot of examples to show the computer, when you see, this situation, I want you to do Y. When you see this other situation, I want you to do Z. Or if there's too many edge cases or it's too complicated to describe with a set of rules or math, so the peanut butter and jelly sandwich is an example of this. There's too many rules for how to pick up a knife and how to hold the knife and get the peanut butter out of the jar, that it wouldn't be a good fit for traditional programming. And in addition to having the data, it has to be informative. So there has to be some kind of pattern in the data. You don't necessarily have to be able to see it as a human, but there has to be some pattern that relates what the computer sees to what it does. Conversely, if you don't have a lot of data, you either need to get the data or machine learning is probably not the solution you want to go for. Or if something can be described simply, like a couple if statements or rules, there's no reason to go reinvent the wheel. Machine learning is great, but if you can do it in a simpler way, you should do it that way. Or if your data can't teach it how to solve the problem, it's also not going to work. So a little more specific, I mentioned identifying cats versus dogs. So image identification in general, machine learning is really, really good at. There's competitions for, it's awesome. And also humans are really good at this. You can look at a picture and quickly decide, yeah, that's a cat or a dog. But how would you describe what you're doing? Like, is it the shape of the ears? Is it the length of the dog's nose? But then what about a bulldog? That's got kind of a stubby nose like a cat. But computers are really good at this. A bad use case would be solving a math problem. You look at this, and I don't know what the answer is. Well, I know because I wrote it down. It's about 42. But you look at this, and you have no idea what this is. I have no desire to solve it myself. But computers are really good at this. We have these tools. They can solve math problems. There's no reason to go out and find machine learning to teach it to do math. Computers are already very good at math. So an oversimplified guideline that I've heard, and I really like, is that if a human can assign a label or a value to something in less than a second, it could be a good candidate for machine learning. So something that's like a quick gut decision that you just kind of know, it's X, it's a dog, or it's a cat. So if you're ready for a change in mindset, and you've looked at what you have, and yes, machine learning is still a good fit, the next thing to do is actually prepare your data. So making sure that you have enough data to train, and is your data clean and ready. So data preparation is new if you're used to traditional programming, and it's important. It's going to feel weird if you're used to spending all day programming, that now you're editing images or sorting files. But managing data is really important. And to illustrate that, there was a survey by Crowdflower. They talked to about 200 data scientists, and they said they spend 50 to 80% of their time just preparing their data. And they also said it's their least favorite part of the job. So humans being humans, they would not be doing this, especially not so much, if it weren't really, really important to the success of what they're trying to do. And so part of the reason this is so important is that your data is going to determine the accuracy of your model, how well this works. You may or may not have heard, if you hear anyone talking about garbage in, garbage out, that's what they're talking about. If you feed your algorithm garbage, it's going to learn garbage, and it's going to give you garbage. So some things that can go wrong are finding an accidental pattern instead of what you want. And so my favorite example of this is there were people trying to teach the computer the difference between a husky and a wolf. It can be hard to do. They're pretty similar looking animals, and they thought they had it. They trained their data, they tested it, and it was really, really accurate in telling the difference between a husky and a wolf until they started looking at how it was making those decisions, and it hadn't learned the difference between a husky and a wolf. It was a snow detector. That almost all of their images of wolves were in the snow, and huskies were usually in someone's backyard. And so it had no idea what a wolf was, it just knew what snow was, and this was not at all what they were trying to identify. So it's the type of thing that, if you're not careful, can creep into your data, and you might be creating a system that does not do what you actually wanted it to. Can also be confused by bad data. So if your labels are wrong, like you just maybe crowdsource something off the internet using, if you're looking at images, oh, people labeled these Google images this way. But if they're not accurate, you're again teaching it garbage and learning those wrong labels that other people have given it. So your data is also going to determine what type of machine learning you do. So there's so many different models, and they're usually what gets talked about when you talk about machine learning. There's this model, and it learns in this way, and it does this. But which one you choose is going to be driven by your data. Do you have enough examples to support this model? Do you need a model that will sort your data into different categories or classes, like dog, cat, wolf? Or do you need something that assigns it a value like temperature or money or time? Or sometimes do you not even have any labels at all and you just want to see, what's in my data? How can I sort things that are similar? So all of these things are determined by your data, and that's why it's such a really important part of this. So when you're preparing your data set, some things to keep in mind. Having enough data, that it has to be accurate, and it needs to be relevant. So you need to make sure that you're giving the algorithm useful information to the problem you're trying to solve. So a really extreme example is that if you want to teach it to identify, a cat versus a dog, pictures of houses in your data set probably aren't helpful. Unless you also want it to identify this is not a cat or a dog, which is, another decision you have to make. Do you care if your system, is your system going to get any weird, unexpected data, and you're going to have to account for that? If you know you'll never get a picture of a house, there's no reason to do that. But if someone could upload one, and you don't want them laughing at your system because you said it was a cat, you might want to include that as an example of not a cat or not a dog. And so this is where subject matter experts are going to be helpful. If you have access to anyone who understands the data and understands the problem, they don't have to be a machine learning person, but if they understand what you're trying to do and how a human might make those decisions, they can help drive your data decisions. What data do you give the algorithm? How do you try and train it? And then your data also has to be complete. You can't have missing information. So for example, medical records, if a person's age is missing, most algorithms don't know what to do with not a number or blank entries. So you want to find some way to fix that, whether that's removing any example that's missing data, or if you can find ways to fill in or guess at what it should be with like the mean value or the median value of that column. But you need to find some way of accounting for any data that's missing. And as I mentioned before, you also have to cover any examples you expect to see. So whenever an algorithm gets data that it hasn't been trained on, there's not a good way of predicting what it's going to do. It's probably going to take the closest thing it's seen and go with that. So if you give it a wolf and it's been trained on cat and dog, it'll probably say dog because they're similar. But you can't always guarantee what it's going to do when it gets something unexpected. And so we talked a little about your type of data determining what algorithm you choose. So if you have labeled categories like cat, dog, true, false, red, green, or blue, you're going to want to be looking into classification algorithms. If you're looking for a number or value like price, temperature, or time, you're going to want things that do regression, so it gives you a continuous value. Or maybe you have no labels. So this gets a little more interesting. It's clustering or unsupervised learning. So it can be good for data exploration or trying to group pieces of data that are similar together. But if you ever want to make predictions on new values, you're going to have to find or make labels somehow. So if you don't have labels, you either need to get them or just be okay that you're just exploring your data. So we're still not done with the data because we have it, but we need to make sure we use it appropriately. So whenever you're doing machine learning, you're going to need to split your data into 2 to 3 categories. So we typically call them the test set, validation set, and training set. So the training set is the biggest chunk, and it's what you train your algorithm on. And this is the only data the algorithm ever sees. You don't train it on your validation set, and you don't train it on your test set. The validation set is used to, you train it on your training set and make predictions on the validation set and see how many gets right. And you can use that to compare different algorithms if you want to see, there's 5 algorithms I think might work. I want to see which one works better. And then once you've picked the best one, you test it again on your test set. And this is your final estimation of, if I put this into production, how well is it going to perform? So you can think of it sort of like when you were in school. The training set's kind of like homework. You have a lot of examples. You're learning what to do. The validation set's maybe a practice exam. You want to see how well your algorithm might be doing. And the test set is that real exam. How much of this information did you learn? So if you put the same questions or examples in the test and the homework, you're not testing its ability to learn the actual information. You're testing its ability to memorize a few questions it's already seen. And so you want to make sure you never do anything to bias your test set or tweak something weird because it gets you better answers in your test set, because it's not going to fool the production system. And then you're going to have to figure out why, when you test it, you get great results, and as soon as you push it to production, it fails. So never mess with your test set. So we've talked a lot about this, but what does it actually look like if you're going to code it? Because we are programmers. So first, you want to import train test split from scikit-learn. It is scikit-learn, if you're not familiar with it, is an awesome Python library for machine learning. Most of the hard things it does for you, it is glorious, and you should look into it. So we want to get some data. You would never actually hard code your data, but I'm giving a presentation, and it's just easier to visualize this way. So X are our examples. We have 5 values. Each is a pair of numbers, so maybe a set of coordinates. And then Y are your labels. So we have 2 different categories. It either belongs in category 0 or category 1. And then if you want to use this train test split, you pass it your examples, you pass it your labels, you tell it how large you want your test size to be. So I want 25% of my data in my test set. And then it gives you your training data, train X, train Y, and your test data, test X, test Y. So before moving on, let's talk a little more about this example data and just show some examples of some of the problems I'd mentioned. So we have 5 examples. The first 3, the first number is larger, and they belong in category 0. And the last 2, the second number is larger, and belongs in category 1. So these labels look like categories, so we'd probably use classification if we were actually using this data. But some problems with this data: there's obviously too few examples. A ballpark number is maybe about 50. If you don't have at least 50 examples, you need to get more or find something that's not machine learning. We've also got some missing cases. Like, what do we want the system to do if the numbers are equal? But also, in addition to that, our goal is unclear. So does a label of 1 mean the second number is larger? Or does it mean that the numbers are sequential, 2, 3, 8, 9? So we don't have enough. In the real world, we don't have enough data to actually train a useful algorithm. But we're going to go ahead with this anyway, because it's just a toy example. And what does the rest of our code look like? So we have our train test split. We split our data. Now what? So from scikit-learn again, you want to import your model. And they have a ton of different machine learning models. Most things that you'd want to do, you just import some library from scikit-learn. So this in particular is SVM. It stands for Support Vector Machine. It's a pretty good classification algorithm if you want to sort things into groups. And if you're just playing around, it's also a pretty good place to start. So if you want to create your classifier, every classifier will have some kind of creation method. So this is svm.svc. You might have some parameters to pass in, but you create an object using that library that you imported. And then to train it, you have that model, and everything in scikit-learn should have a fit function. You pass it your examples, your labels, and that is all there is to actually training the algorithm. So another part of the reason I spent so much time talking about the data is because actually training the algorithm is this. This is really all there is to it. And so to evaluate your model, you can import different metrics from scikit-learn. So here we're looking at the accuracy score. And then to make a prediction, the model, in addition to fit, also has a predict function. So you pass it some more examples. Here I'm passing it our test set, and it'll give you a list of what category it thinks each of those examples belong to. And then if you wanted to calculate the accuracy, you would use accuracy score, pass in what it's actually supposed to be, the real labels, and all of its predictions. And so this will tell you what percentage of the test set did it get right. So that's it. We've trained a model, we've evaluated it, we have accuracy. What else do we have to think about? So back to the final new part of the mindset, how to decide whether or not it works. There's a lot of different metrics to decide, how well is this performing, and do I need to make it work better? So this is just a few common ones, but for classification, accuracy is a huge one. Just what percentage of the time am I right? But you also have things like precision. Of the things I said are dogs, how many are actually dogs? And there's also recall. So what percentage of dogs did I find and actually label dogs? And they sound really similar, and so that's also part of getting used to machine learning, is coming to grips with what these mean and their distinctions and when you would use one versus the other. So for example, in my work, we use a lot of precision because we only accept things that the classifier is really confident at. It's like, yeah, I'm pretty sure this is right. And so we're mostly interested in, if I bothered to give a classification, did I get that right? Whereas we're not worried about the total percentage as much as some other people might be. And so if you are worried about just the whole overall, you don't drop anything, we include everything, then you'd be more interested in accuracy. It's especially important in medical situations. So if you're testing for a disease and you want to make sure you don't miss a single person who has that disease, they all come up positive, then you have to balance how many people who don't have the disease also come up positive. And so that's one of the places where that's really going to come into play. And so I didn't talk much about regression or trying to predict a continuous value, but some common methods are the R-squared score, which is exactly what Excel would give you if you put a bunch of data in it and tell it to plot a line. That's the score it gives you back. So if you've ever done that, you've already done machine learning. There's also something called the mean squared error. So for each prediction, you take how far off it is from the value it's supposed to be, square that, add that all together, and that'll give you a sense of how well your algorithm's performing. So a recap of everything we've talked about, because I feel like I went through a lot and talked a lot about data. But if you find yourself suddenly needing to learn machine learning, just kind of get prepared to have a new mindset. It is different from traditional programming, but it is a lot of fun. Make sure you determine that machine learning is the right solution for your problem. Don't let people talk you into using the new buzzword just because it sounds cool. It might not be the best solution. You want to clean and prepare your data, and then a subcategory of that is, depending on your data, choose the best algorithm to use, and then try it out, see what happens. If it works, great. If it doesn't, try something a little different. Maybe you need more data or different data, or maybe you need a different algorithm. Just play with it and see what happens. And then there are a lot of resources on machine learning. I tried to pick some that were a little more introduction friendly. So I enjoy the Practical AI podcast. It's a podcast, so it can't get super technical, but it can introduce you to ideas at a higher level. Scikit-learn, the library, has some great documentation, not just on how to use their functions, but also what they're for and how you might want to use them. If you're more interested in things like neural networks and deep learning, 3 Blue 1 Brown has an awesome series of videos on how neural networks work. He tries to be very intuitive. I love all of his videos, actually. You should check them out. And then there's a website on neural networks and deep learning that's more technical but walks you through building your own neural network. Pythonprogramming.net has some stuff on machine learning. And then there's a ton of Coursera courses. The one I thought was particularly interesting was Andrew Ng's course on structuring machine learning. This one's a little more on how you would structure the project itself rather than the technical details. But there's a ton more resources out there. This is just kind of to get you started. I hope that was helpful, and I'd be happy to answer any questions.
Awesome. So I know we have one from Slido that Josh picked up. We're going to get that fixed again, but Josh has got a question from Slido for you. Actually, here, I'll let you.
So the question is, communicating estimates or forecasts is difficult in software development. How do you have that even more challenging conversation around machine learning?
Yeah, so that is a lot of fun. And actually the way that we approached it was gave the people who had trouble, understanding. We actually put together a presentation on the very basics of machine learning, which is this is loosely based on that actually. But we went into a little bit of detail on how the algorithms we're using work and why it might be slow. But it was a lot of education, because once they had more of an idea of how it works and why it's different and why it's not magic, they were a little more receptive to oh, I know it'll take time because the computer needs to train it for a while, and we have to, after that we have to see if it even works, and maybe we have to clean out our data. But it was a lot of education.
Any other questions for Alyssa? Oh, we got lots of questions. Awesome.
Got a question about in a business. If you were joining a new company that didn't do a lot of machine learning, would you start off by proclaiming the benefits of machine learning, teaching everybody how to do it, getting all these marquee projects, or would you start off by doing it kind of on the low key and then presenting the results? Because you don't know necessarily whether or not you're going to make a big impact with your problem, and people might be turned off on it if it fails, or there might be a short runway for doing machine learning. So how would you tackle it in a big enterprise?
That is a really good and complicated question. So I've sort of seen both methods and seen mixed results with both. So it's if you can get the support. So I guess your best case scenario is if there's no other way to do it. So if you're trying to identify images of something, there's no other way to do it. So you have your use case, we have to use machine learning if you want this to happen. I have seen people work on things below the radar, and it never pans out, or people think it's going to pan out, but because there's only one person kind of in their little cave working on it, people aren't in the loop and they don't know what's happening. And so if it winds up not working, it could be that could actually be a surprise to people, because you're oh, I'm working on this thing, and then it doesn't work, and everyone thought it was going to eventually. So it can be a really tough balance, but I would definitely recommend doing everything kind of in view of everyone and making it actually a part of the process. And if you're in an organization that's not wild about the timeframes and stuff, we've definitely done some things that would have been better with machine learning, but because you could hand code it, we did. And I still, yeah. It is very case by case and very strange, but if you at all can, I definitely recommend getting everyone on board and just like the training is part of it. So we do like Agile Scrum, and we have so many research spikes. It's like this sprint, we're going to see if this thing works. And so that has gone pretty far away into getting people to accept it. They're just like, oh, you have a weirdly large number of research spikes, but they sort of got used to it. But yeah, it is complicated and good luck.
I have a question over here.
So I'm a little iffy on the need to define the validation versus the test set. Like I'm gonna run precision, accuracy, and recall or a confusion matrix in any event. Why would I not just compare the algorithm performance on the test set itself?
So there's also the question of what is the best practice and what can you get away with, because sometimes you can get away with not having a validation set. But the real purpose of it is getting any bias out of your decisions. So if you are comparing, a bunch of algorithms and you compare them on your test set and you pick the best, you have picked one based on its performance on that set. So if it just happens to perform really well on that set of data and you don't test it on a separate set of data, the fact that you picked the best performing one can bias how it would actually do, because you could be, if you're only testing a couple things, it's less of a problem. But if you tested and compared 1 million examples, the probability that one doesn't actually work well, it just happened to work well on that set of data, goes way up. And so the idea of having a separate test set is you could catch that if it, I picked this because it did well in validation and it tanks on test, it must have been something really weird with why I chose that. Was that a reasonable explanation? Okay.
I think we had a question, another question on Slido.
Yep. So David asks, how do you decide between traditional machine learning algorithms and neural nets?
So neural networks are good. There's some things that are like neural networks are definitely the best at. So anything with images or anything where you need the algorithm to determine its features. And so I haven't talked about features explicitly, but they're what you decide to give the network to train on. So pictures of dogs and cats, there's no features there, it's just a picture, and it has to learn what to look for ears or nose or color. But if you're giving it, like you want to know housing price and you give it the square footage, the number of rooms, those are all features. So if you want the algorithm to learn features, neural networks are great for that. If you have a lot of data, neural networks are great for that. But they do require a lot of data to train. And so if you don't have as much data, you would probably have better results sticking with traditional machine learning. Or if you don't want to sit through the time it takes to train a neural network, because they are slower to train, traditional methods are usually faster, and a lot of them, but not all of them, are more explainable. So if it's important that you can explain to someone why it made a decision, neural networks are a terrible idea.
Regarding deep learning specifically, what would be your approach if I just wanted to become comfortable with setting up neural nets? And do you have an opinion on like PyTorch versus TensorFlow versus whatever else is out there on that?
So my personal favorite is Keras, which definitely wraps TensorFlow, and it might wrap, it's kind of like a wrapper for a couple other backends. But the main reason I like it is because usually what I do if I'm working with images, you can actually download straight through Keras a trained model that has already like there's Google's model that they put in the ImageNet competition. You can download that, and then you can do what's called transfer learning. You pull off their labels, because I don't care if it's a cat or a dog. I put on the labels that I want, and you don't need nearly as much data or as much time. You just train that end layer a little bit. So that's one of the main reasons I like Keras. It's just really easy to work with. But a lot of it's preference. Like if you are reading about something and you like the way it works, or the way they handle code, it's definitely never a bad thing to learn any of them. And once you learn one, the others are going to be a lot easier. Was there another part of your question? Because I just remember the keras part, or the TensorFlow part.
Generally, like where would I, like what's, like, that's, like, aside from personal learning style, what's the best way to just learn how to do this if I'm not walking in with a test set that somebody's given me?
Okay.
Can you repeat that part for the recording?
So I think the summary is, if you don't have your own data set and you just want to learn, what is the best way to kind of get started? So Kaggle is pretty good for this, that they have data sets that you can use and have kind of organized competitions. I really wish I remembered the name, but there is another like data set repository where you can upload a data set for anyone to play around with. So yeah, if you can find data sets on the internet or through Kaggle to kind of like give you a pre-made goal to try. And for neural networks, for general understanding, I like 3 Blue 1 Brown's video, and then there's a couple courses like neural nets and deep learning, and a couple on Coursera that will walk you through how to build your own network. And so a lot of them start with like building it from like the individual neuron, but it's good background, and by the end you'll have something you can use. So I like a lot of stuff like that.
Hi, yes. So within the context of small data sets and traditional machine learning, getting started, what metric are you looking for in an ideal like project-based setting? Like, are you looking to chase metrics based on confidence? Like, do you get better results that way rather than having to make a definitive choice? Like, at what point do these small data sets express better performance in one environment, say, where you're willing to drop off and give no answer versus give an answer and you're now dealing with like outliers and things?
Okay, so let me make sure I understand the question before I answer it. So you were asking about the differences between, so with traditional machine learning and small data sets, differences between when you force it to always give an answer versus when you can say, I'm not confident enough, I'm not giving it. And the question was like, just general differences or? Okay, and then the question was, what are the trade-offs on that? So the advantage to being able to say, I don't know, comes when you are not necessarily, when you're more penalized for giving an answer and being wrong than for not giving an answer. So if you have a backup system, so for example, if you're, like if you're automating data entry and you have some humans to back you up and you're just trying to make their job go faster by taking the bulk of it, you can say, I don't know, give it to the human, you've done nothing wrong. If you have no backup system and you absolutely have to make a decision, so like in a self-driving car, I don't know is probably never an acceptable answer. It's not a small data set, but the same idea kind of applies. Like if you have a mission critical decision and you have to make a decision, then being able to say I don't know isn't really an option. One workaround could be, if you don't know, to kind of try something else to get a decision. Like, oh, my network isn't confident, but I can turn on a couple extra sensors, or I can try something different. If that's a possibility, that's something you could do. But yeah, a lot of it comes down to like, is I don't know an acceptable answer? Because there are a lot of advantages that come if you don't have to give an answer. Then you can be a lot more accurate, because if you're not sure, you just won't say anything.
I got time for like 2 more questions.
I was just actually going to make a comment about the question on how to introduce machine learning to your company. One of our executives is trying to do that in our company, and he passed around a podcast called DeepMind. It was a really interesting podcast where they're interviewing this foundation or company, organization really in London that started this, and then Google ended up buying them. But it's just some jaw-dropping inferences that have been developed by machine learning that gets people excited about it. And it's kind of catching on in our company. It's kind of a neat way to introduce it.